Okay, on to question 3 from this year's DEB mock exams. So the very first question gives you these two complex numbers, a over 1 plus I, which is z1, and z2, which is b over 1 plus 2i. It says that if you add these two numbers together, you should get 2. And from that information, can you find a and b? Well, let's look at z1 first, which is a over 1 plus I. So anytime you see a complex number with the imaginary in the denominator, you should always be thinking about the complex conjugate method, which is multiplying by the conjugate of the bottom part over itself, something like that. And that will actually give you, it will get rid of the imaginary number on the bottom, and it will give you just a regular complex number with just an a plus bi. You may have fractions in that, but it'll be okay if we get there. So let's do this first. So a times 1 is a times minus I is minus ai, over 1 times 1 is 1, and then we have 1 times minus I, then we have I times 1, then we have plus I times minus I, which gives us a minus I squared. Now we're always looking out for this guy here, this I squared, because we have to remember that I squared is equal to minus 1, and always change when you see that. So these two guys in the middle are going to cancel. It's going to give us this, a minus ai over 1 minus, and I squared changes to minus 1. So that's going to be a minus ai over 1 plus 1, which is equal to a minus ai over 2. So there's our first one, and we have no I on the bottom. Same for the second one. So for z2, we have b over 1 plus 2i. We're again going to multiply that by its conjugate on the bottom part over itself. So the conjugate's just where you change the sign in the middle only, or change the sign with the imaginary part when it's written like this. But we're not changing the 1 to a minus, just a mistake that can be made. So again, b times 1 is b, and then minus 2b and an I, these things together. 1 times 1, and then minus 2i is plus 2i, then a plus 2i by a minus 2i gives us a minus 4i squared. Again, we have this I squared, so bi. So these guys always cancel. And then we have 1, and we have minus 4 and I squared being minus 1. That gives us a b minus 2 bi over 1. What becomes now a plus 4. So this number becomes b plus 2 bi over 5. So there's our second one. So we've taken these two complex numbers into something we can work with. So what have we got now? We have, if the two of these are added together, they sum to 2. So a minus ai over 2, and then plus b minus 2 bi over 5 should be all equal to 2. This is just a simple algebra problem now, so we must look for the common denominator here, which is going to be 10. So I'll just do this in like baby steps. So rather than doing this in one short step, I'll actually multiply everything by 10, just to show you, just in case you're confused with it. So remember, in an equation I can multiply everything by the same number. So I've taken all the terms, multiplied them by 10. 10 over the 2 is going to cancel to be 5, so I'm going to get 5 times a minus ai. The 10 and the 5 is going to cancel to be 2, so I'm going to get 2 times b minus 2 bi. And the 10 times 2 is going to be 20. So when we multiply these in, we get 5a minus 5ai plus 2b minus 4bi equals to 20. Now what we have here is we have some variables, including some imaginary numbers, equal to some real number, 20. So what I'm going to do is I'm going to write it like regularly, a plus bi. This is how we are used to seeing complex numbers, the real part separate to the imaginary stuff. So what I'll do is I'll take the real numbers, that is numbers that have no I attached, away on their own. So that's 5a is going to go at the front, and 2b. So they're all the real things that we have. And then we have minus 5ai minus 4bi, yeah, equals to 20. again, one further step just to see, I just want one I there. What I'm going to do is take I out of here. So I'm going to say minus, I'm going to use brackets 5a. But I'm going to say plus 4b and put an I outside. Now, why did I say plus? Well, if I multiply this minus back in, minus times 5a is minus 5a, and minus times 4b is minus 4b. That's why you see the plus. Now, let's look at what we have. We have this variable stuff here being real, and this variable stuff here being attached to an imaginary number. We only have real stuff over here. The only way this is going to happen, this equation is going to work, is if the real stuff ends up being 20 and the imaginary stuff ends up being 0. That's the only way that can happen. So just to save space, I might just do something over here. So what's happening? Well, 5a plus 2b must be equal to 20. Yeah? And 5a plus 4b must be equal to 0. Because that's with an I and we have no I on the right hand side, this has to go to 0. Now I have two equations and two variables. So it's classic simultaneous equations. To do this, let's change the signs on the bottom. So I'll change that to a minus, this to a minus, and 0 is going to be unaffected anyway, but stick the minus in there. We'll draw our line and we see that we have 5a over minus 5a cancels. 2b minus 4b gives us a minus 2b. 20 minus 0 is just 20. So we see actually that b is equal to 20 divided by minus 2, which is going to be minus 10. That's what our b is. What's our a? Well, we can just put this into the top equation, put b in here for minus 10. So we can take 5a plus 2 times b, which is now minus 10, equals to 20. That's 5a minus 20 equals to 20. Our 5a is equal to, that comes over to become a plus 40, giving me that a is equal to 8. Sorry, I had to squeeze it in at the very bottom. So that's the first part done. A is equal to 8 and b is equal to minus 10. Okay, in part B it says u is a complex number with a modulus of 8 and an argument of 2 pi over 3. And it says v is a complex number 2 root 3 minus 2i. A complex number written like this in like a plus bi, that's known as like rectangular form. Wanting to write it in polar form is the other way. Actually, what you need to write in polar form are two things. You actually do need the modulus and the argument. They actually give us that in the first part, so it's going to be pretty easy. Just as a reminder, a polar form of a complex number looks like this. If some complex number is z, it's the modulus of z times the cos of the angle, which we call the argument, plus I sine of that angle. So looking at the first part, it says for u, it's going to be the modulus of u, which of course gives us 8, times the cos of the angle. So it gives us the angle, and remember angle, argument, interchangeable terms here. So when I say angle, our argument, I mean the same thing. So the cos of 2 pi over 3 plus the I sine of 2 pi over 3. So that's actually u done. V is a little bit more work because we're going to have to find these numbers, okay? So we may need our calculator to get the angle. So let's look at V. So for V, we have a 2 root 3 minus 2i. Now, I always believe it's good practice to draw a small sketch of what we're dealing with here. So a coordinate diagram for a complex numbers is known as an Argand diagram. So you have the y-axis is the imaginary and the x-axis, you know, is the real. So where are we? So we're out 2 root 3 is a real number. So we're out this way here. And then we have to go down minus 2i here. So our number's here somewhere, v. So what we need first is the modulus. Now, the modulus is effectively the distance back to the origin. And we can deal with these as regular numbers. So there is a formula for this, but using Pythagoras' theorem you can pretty easily get it. But the formula essentially is Pythagoras' theorem. So for the modulus of v, so straight lines around v means modulus, we have the square root of the real part squared plus the imaginary part squared. So the real part squared, what's that? That's 2 root 3 to be squared, and the imaginary part is minus 2. So one important thing here is that we would never include I here. just in case you're tempted to. Never include I. Right? So let's do this, and then so this stuff squared is going to be a 4 and a 3. That's going to be 12, and minus 2 squared is going to be a 4. So that's the root 16, which is of course 4. So our modulus is 4. Next we need the argument. Now this is where it gets a little bit trickier. Why? Well, the angle, if we look at where the number is, goes back to the positive x-axis, unless you want negative angles. So it's kind of good practice just to deal with the positive angle. We're also dealing in radians for these angles. Now, remember that pi radians is 180 degrees, meaning 2 pi must be the 360 degrees. So we have somewhere here, we're nearly all the way around, not quite as far as 2 pi. But what we're going to do here is, we're actually going to check and see what this angle is here, theta. So let's draw this triangle here, just separate for the argument. So the triangle I'm dealing with, where the angle looks like this. So where I came down a length of 2, you can disregard the negative sign and the I here. And I came out a length of 2 root 3. And I'm looking for this angle theta here. Well, by our trigonometric ratios, we can see that this angle has an opposite side and an adjacent side. Where this has been a right angle triangle. So opposite and adjacent, well then we're dealing with tan. Because remember the tan of theta is equal to opposite over adjacent. So then we can say then the tan of theta is equal to the opposite side, and the opposite side the angle is looking at, 2, over the adjacent side, which is 2 root 3. Okay? So effectively then theta must be equal to tan inverse of that stuff. Now they cancel, of course, just give me a 1 over root 3. So I have to get the tan inverse of 1 over root 3. So I'm going to make sure my calculator is in radians by going to shift mode, and then radians being number 4. Okay, and I go shift tan inverse and 1 over root 3 and equals, I'm in radians, and I got a value of 1 over 6 pi, which is the same thing as just pi over 6. But of course that's not the angle I'm looking for. That's the angle in here is pi over 6. I'm looking for the angle all the way back to the positive. Now remember what I said, 180 is pi, therefore 2 pi is all the way around. So I'm gone around 2 pi, and if you like, back that angle of pi over 6, which is this angle here. So actually my angle, my argument is going to be 2 pi and then minus pi over 6. So if I actually do that, I get 11 pi over 6. You can simply just put this into your calculator, it'll give you 11 pi over 6. So the modulus for v is 4 and the argument is 11 pi over 6. So to write it in polar form, we need the modulus and the argument. So therefore v is equal to, and then the modulus being 4 times the cos of the argument, which is 11 pi over 6, plus I sine 11 pi over 6. There you have it. That's part B done. Now we're on to the final part, and the final part says, use De Moivre's theorem to evaluate u over v to the power of 6. So we have u over u and v from the last part in polar form. Now just to remind you of De Moivre's theorem, if you have a complex number in polar form, like z is equal to the modulus of z times the cos of some angle theta plus the I sine of some angle theta, well then z to any power n, like any number you want, you put the modulus to that power and you multiply each angle by that n. So, oh, n in there, not a little n, sorry. So essentially what we have to do here is, first off we have to find u over v. Now, and we have to use this then to solve it to the power of 6. Now there's a nice little identity, if you like, that we can put two polar numbers together. And what we have is in division. There's also one for multiplication, but just to keep the video not being too long, I'll just deal with the division one. So it says that if you have two complex numbers divided like this and they're in polar form, you can actually just divide their modulus numbers and then you can subtract their angles, being the one on top, its angle, subtract the angle from the bottom. So what does that look like? Well, u over v is going to look something like this. The modulus of u over the modulus of v times the cos of, we'll say, theta u minus theta v. So I mean this angle subtracting this angle, plus I sine of theta u minus theta v. So we literally divide the two modulus and we subtract the angles in this particular order, being the top angle subtracting the bottom angle. So for us that looks like this. What's the modulus of u? 8. The modulus of v? 4. The angles. Cos of the angle of u is 2 pi over 3 minus the angle of v, which is 11 pi over 6. And it's the same for the other side. Those of you that are a bit more astute might notice that you can just change this to 4 pi over 6. Those of you that want to insist on using a calculator, which is a great idea because you'll eliminate any arithmetic mistakes you might make, just literally, I'll just do that in the calculator and see what I get. 8 over 4, I hope we all know is 2. So the cos, so what do I have? So you have to excuse my calculator, I'm sorry. 2 pi over 3 minus 11 pi over 6, and that should give us minus 1 1/6 pi. So what's minus 1 1/6? That's minus 7 over 6. So minus 7 over 6 pi plus the I sine, it's going to be the same stuff here, minus 7 over 6 pi, like so. So we're down here so far, but remember, we can't forget that we actually needed all this stuff to the power of 6. So we could take this stuff here and use the Moivre's theorem now to put it to the power of 6. So what's that going to look like? Well, at the front it's going to be 2 to the power of 6 by the Moivre's theorem, that comes in. And then the cos of 6 times minus 7 pi over 6 plus I sine 6 times minus 7 pi over 6. So everything I've done in red pen here has been as a result of using the Moivre's theorem to get this up to the power of 6, right? So if I just wanted u over v, I would have been finished here. But now I wanted it to the power of 6. So what's 2 to the power of 6 going to be? 2 to the power of 5 is 32, so 64. Now, this is going to be the cos. These 6's are going to cancel. Giving us minus 7 pi there, plus I sine minus 7 pi. So actually, when we go down here, we get 64. Let's get the cos of minus 7 pi. So the cos, again, we make sure our calculator's in radians. Minus 7, I don't need the fraction. Minus 7 pi, close. So the cos of minus 7 pi is minus 1. Plus I times, and we'll do the sine of minus 7 pi, and that gives us 0. Lovely. So 0 times I goes 64 times minus 1 is just minus 64. So the answer to this big long problem actually just ends up being a complex number with no imaginary part, just minus 64. That's it.